I'm Professor Rad, and this is Precalc video 2.6, factoring techniques, factoring a polynomial. So in this video, we're going to do two examples of factoring some polynomials. Well, one, we're going to factor a polynomial, and then the other one, we're going to use it to solve an equation. But in both cases, we're going to be applying these steps for factoring a polynomial. So when I first started teaching, my good friend Tina gave this beautiful pointer to me. So Hello Kitty is going to help us out today. So for our first step of factoring a polynomial, we're going to use the rational zeros theorem, and that's going to give us our rational root candidates. Then for number two, we're going to use the factor theorem to check those candidates. Now, if you wanted to, you could check all of the candidates, but depending on how many candidates you have, like I think in one of our examples, we had like 20 something. So that could take a while. So what I typically do is I check my candidates till I get one, and then I proceed to the next step. So once you have a candidate, you can apply synthetic or long division. So take that candidate and then divide it out. So you can factor out that, and that'll give you a new polynomial. And then you have your choices. You can repeat this process, or you can apply some other factoring techniques. So for example, I have over on this board some common factoring techniques. So these are ones that you are expected to know. So we have the difference of two perfect squares, a squared minus b squared, is going to factor into a plus b and a minus b. And then the difference and sum of perfect cubes are going to factor into one linear factor and then one quadratic factor. So you can apply those factoring techniques if you wish. And then after you apply those techniques, you can then repeat this process and check for more of your candidates and continue to do that. And then once you've exhausted all of your rational roots and all of your factoring techniques, then you can check for complex roots. So for example, that's usually going to be what we need to do when we have a quadratic factor like this one showing up in the sum or difference of perfect cubes. So usually we're going to be using our complex roots for that. So you'll likely need your quadratic formula for that, or you can complete the square, or maybe you get something that's not so terrible to factor and find the complex roots. So let's do an example first of factoring completely, and then we'll do a second example where we apply factoring to solve an equation. Oh, excuse me, we'll solve an equation. All right, so let's get to factoring. For this example, we've been asked to factor this degree 5 polynomial. I've written it out in standard form just to help us as we go along. Now, the first thing that I notice before I apply these steps over here, before I apply these steps over here, is I notice that each of these terms has an x in it. So I'm going to begin by factoring out an x, and then I'll apply the rational root theorem. So let's take out an x. By the way, taking out an x is good math advice, but terrible dating advice. Do not recommend. And when I factor out that x, we get 2x to the 4th minus 9x cubed minus 2x squared plus 39x minus 18. All right. There's no other factor in common for each of these terms, so we're going to progress to our steps. So the first step is the rational root theorem. For the rational root theorem, this is where you find the C over L stuff. So we're going to find C over L. Recall that C are factors of our constant term. So in this case, that's going to be factors of 18. So that's 1, 2, 3, 6, 9, and 18. And then for L, we have 2. That's our leading coefficient. So we have factors of 2, which are 1 and 2. Now, it's up to you how you want to go about this. You can find all of the candidates and then check all of the candidates you find. And that may bring you to factoring this completely. But what I'm going to do is I'm going to do a partial list because I don't want to do more work than I have to. So what I'm going to do is I'm going to check 1 over each of these two and see what we get. Also remember, every time you do this, whatever positive roots you find, you also have to check the negatives. So I'm going to find 1 over 1, 1 over 2, and then the negative forms of that. If I find a rational root, awesome. If not, then I'm going to move to 2 over 1 and 2 over 2. And then I'm going to keep repeating until I find a rational root. So to begin with, I've got 1 over 1, which is 1, and 1 over 2, which is a half. And then I also have to check the negatives when I get there. So to see if any of these are a rational root, I'm going to substitute them into this polynomial here. So when I substitute in 1, I've got 2 minus 9 minus 2 plus 39 minus 18. Oof. Okay, so 2 minus 2 is 0. Negative 9 plus 39 is 30. That's not going to give me 0. So that one's out. Oh, crud. 1/2. Okay, so we're going to get 2 times 1/16 minus 9 times 1/8 minus 2 times 1/4 plus 39 times 1/2 minus 18. So I'm getting these by raising 1/2 to each of those powers. And I don't feel like dealing with fractions right now. So yeah, rely on some technology to help me out here. So we're going to have 1/8 minus 9/8 minus 1/2 plus 39 halves minus 18. Ooh, that gave me 0. Okay, so 0 is what we're shooting for, because when you substitute in by the factor theorem, if you get 0, that means that you're going to have a rational root. So just because I'm limited on space on my board, I'm going to erase all of this. And I know that 1/2 is going to be a root that I can take out. So let's do that. So I have my x. I'm going to factor out x minus 1/2 because 1/2 was the rational root I just found. And to figure out the cubic that I'm going to be left with, because I'm taking out a degree 1 from a degree 4, so I'm going to be left with a cubic, let's do some synthetic division. So I'm going to put all of my coefficients here inside the box. 2, negative 9, negative 2, 39, negative 18. And I'm going to put that 1/2 on the outside. And no, here's hoping we don't have too many fractions to deal with, because I don't want to do that much mental arithmetic this late at night. So 1/2 of 2 is 1. And then negative 9 plus 1 is a negative 8. 1/2 of negative 8 is a negative 4. Minus 2 is negative 6. 1/2 of negative 6 is negative 3. Plus 39 is 36. 1/2 of 36 is 18. And we'll get our remainder of 0 as we anticipate. This is degree 0, 1, 2, 3. So we know that we're going to have 2x cubed minus 8x squared minus 6x plus 36. All right, and now I can erase all of this stuff since we've used it. If I were doing this on paper, I wouldn't erase it. By the way, I'm just doing that. So I have some more space to continue working on this problem. Now, one thing you may notice is that each of our coefficients here is even. So when that happens, I think that happened because we had this fraction here. So if I wanted to, I could factor a 2 out of this factor here, and then distribute it into this factor to get rid of the fractions. So, you know what, why don't we do that? So what I'm doing, I'm going to keep this first one and this second one the same. And then I'm going to factor a 2 out of this big long factor here. So that'll give me x cubed minus 4x squared minus 3x plus 18. Then I'm going to distribute this 2 into this factor here. So that will give me x times 2x minus 1, and then x cubed minus 4x squared minus 3x plus 18. Okay. So now we have our x, our 2x minus 1, and then we have this cubic. I don't know much about this cubic. It doesn't fit any of our special forms. So we've done our division, and now we're going to repeat. So we're going to repeat this process. We know that we can continue to repeat this process, that we're not done factoring yet, because this is cubic. And we know that if we're factoring completely over the real numbers, that it will eventually dwindle down to linear factors and quadratic. So we can break this one down further. So let's do our C over L's. So we've got our new constant term is the 18. Put it over here. So that's 1, 2, 3, 6, 9, 18. And our new L factors are factors of 1. So L is going to be 1. Okay, so I know from my work before that positive 1 did not work as a factor of this beast. And if it didn't work as a factor of the big beast, it's not going to work for the factor of the little one. Otherwise, it would have worked for the big one as well. So I know that 1 isn't going to work. So I can try 1 over 1, doesn't work. Let's try negative 1. So if I throw negative 1 into this, that's going to give me negative 1 minus 4 plus 3 plus 18. So that's 21 minus 5. Nah, that won't work. So next we'll try 2 over 1. So 2 cubed is 8. 2 squared is 4. So this is minus 16 minus 6 plus 18. Let's see, 8 minus 6 is going to give me 2. 18 minus 16 gives me 2. Oh, nope. Positive 2 did not work. We had a 2 over 1. Let's try negative 2. So we'll get negative 8. Negative 2 squared is 4, so we'll still get minus 16 plus 6 plus 18. All right, negative 8 plus 6 is negative 2. Negative 16 plus 18 is a positive 2, and that gives us 0. All right, so when we substitute negative 2 in for x, we ended up getting 0. So by the factor theorem, that means that x minus negative 2 will be a factor. So I'm going to write that out on the side. So we bring down the x, bring down 2x minus 1, and now we're going to add x minus negative 2, which is x plus 2. We're going to add that to the mix. And we're going to have a quadratic after we do some synthetic division. So let's try some of that off on the side here. So I'm going to put negative 2 outside the box and these coefficients inside the box. And I'm just going to zip through this since we've already done some synthetic division in this video, but you can kind of work through it slowly and pause to check your answer if you like. So I'll give some negative 2. So this is going to give us x squared minus 6x plus 9. All right. So now we have linear factors and we have one quadratic. So if you wanted to see if this would factor over the real numbers really quickly, if you didn't recognize its form, you could find the discriminant. Remember, if the discriminant, b squared minus 4ac, is positive or 0, then you're going to get real roots and it'll factor. If it's negative, then you're going to get complex roots and it won't factor over the reals. So in this case, I recognize this as a perfect square form. This is the same as x minus 3, quantity squared. So I'm going to write it that way. If you didn't recognize that, you can use your trinomial technique. We need two numbers that multiply to 9 and add to negative 6. So negative 3 and negative 3 do the job. So that's why we factor there. And at long last, we know we're done because we have factored into all linear factors. So Hooray. Okay, let's do another example. I'll start it out with you, and then you'll pause the video and I'll pause the video, and we'll work on it separately and reconvene to see if we agree with our solutions. All right, so this time, instead of being asked to factor a polynomial completely, instead we've been asked to find all complex solutions to this equation here. Now, just kind of a side note, all real numbers are complex numbers. So when it says to find all complex solutions, you want to make sure you find any real number, so any normal number we work with, along with any complex numbers like 3 minus 2i or I or things like that. When you see an equation that involves polynomials, resist the urge to factor immediately. The reason you want to resist the urge to factor immediately is because we're going to use the zero property as our property to solving. The zero property says if you have a product equal to 0, then each of the factors in that product, like at least one of them has to be 0. And that's how we find our solutions. That's why we factor, because we want a bunch of stuff being multiplied equal to 0, so then each of those individual items is going to equal 0. So the reason I don't factor right away is because I don't have 0 on one side yet. So you pick your poison here. You can decide to bring everything to the right or everything to the left. Because I notice x to the 4th is on the left and it's got a positive coefficient. And I like that about a polynomial to have a leading coefficient that's positive. I'm going to bring these two terms over to the left. So I'm going to have x to the 4th. When I add 2x cubed to both sides, I'm going to get plus 2x cubed. Bring down my plus x squared. Then since we have a minus 8x, I'm going to add 8x to both sides. I have my minus 12. And now we equal 0. So now, once you have a polynomial equal to 0, you can go ahead and apply your factoring techniques to factoring and use that to solve. So this is where you're going to be on your own. You're going to try this one out. Remember that the rational roots that you decide to check may be different from the rational roots that I decide to check first, or that your friend decides to check first. So it doesn't matter. Our work is probably going to look very different, but hopefully in the end, our solutions are the same and our factoring works out correctly. One thing to bear in mind when you're doing your synthetic division is if you don't get a remainder of 0, there are two places you could have gone wrong. You could have gone wrong with your synthetic division, or you could have gone wrong when you were evaluating the root in the candidate in the polynomial. So those are your two places you want to check. If you do synthetic division, you don't get a remainder of 0. Otherwise, I'm going to ask you to pause the video here and try to factor this beautiful quartet. I trust that you can do this. I have faith in you. And when you've got that done, unpause the video and I will kind of walk you through my work. And I'll try not to erase any of it so we can walk through it from start to finish. So I will see you in a little bit. Alrighty, so due to TV magic, I've reappeared right away, but it has been, oh gosh, like 10-15 minutes for me. Maybe it's been the same for you as you worked through this. So for my final set of solutions, I got 1, -3, -2i, and 2i. So I did get 4 unique solutions, which matches one of our previous theorems that says you will have at most the degree unique solutions. So our degree was 4, and we wound up with 4 unique solutions to this equation. So I'm going to walk you through what I did. So I started out off screen here by doing C over L. So I looked at my factors of my constant term, which in this case was this -12. So these are my factors of -12, and then factors of my leading coefficient, which was blessedly 1. So there was my 1. So then I went ahead and I said, okay, 1 over 1 is 1. I substituted 1 in, and I got 0 right away. I was super thrilled with that because you got a factor immediately. So nice. So then I did some synthetic division, and I got x cubed plus 3x squared plus 4x plus 12 in the end. So on this line, you can see that that's where I've done my factoring. I factored out x minus 1, and then I have that cubic. Now, at this point, you could also use factoring by grouping, but I decided to continue with this theme, just in case you didn't notice factoring by grouping. And also to illustrate some of the pain of the rational zeros theorem. Sometimes you just have to remember it's not infinity anymore, it's a finite number of checks. Okay, so, one I had already tried. You could try it again, sometimes you get a double root, but I decided to carry on and went to -1, but I knew this was not going to be 0. So 1/1 and -1/1 didn't work. So now I went to 2/1 and -2/1. So 2, I'm adding a bunch of positives, that won't work. And -2 was kind of close, but the wrong things canceled here. So that did not get me to 0 either. So then I tried 3/1 and 3/-1. So 3 didn't work, but -3 did. I got -27 plus 27. And this time, just to be clear, I was substituting into the smaller polynomial. So this is the one I'm trying to break down. So that's the one that I'm substituting into. Once I saw that -3 worked, I was out of room. So I did my synthetic division on the side here. So I divided the smaller polynomial by that -3. Got this as my solution, which means here's my x minus 1 and then x minus -3, so x plus 3. And that left me with x squared plus 4. Now I know that x squared plus 4 is a smiling parabola 4 units above the x-axis. So I know that that's prime over the real numbers. So at that point, you could try to use your quadratic formula. I knew that I'd be able to use the square root property. So since we're finding solutions here, I set each of those factors equal to 0, and then got x is 1, -3. When I brought the 4 over here, it became a -4. And when you square root a negative, you're going to get that I. And remember, when you take the square root to solve an equation, you need that plus minus. So that's how I got positive 2i and -2i. So there we go. That was my solution for this problem. So that's a lot of factoring. So that's going to wrap it up for this video. In our next video, we are now going to be kind of going backwards a little bit. We're going to say, okay, so we found this polynomial here. We're able to break it down and get some information. What if I want to go backwards? What if I want to tell you information about my polynomial and then you create one for me? So that's what we'll see in our next video. I hope this video helped you with some advanced factoring techniques, and I look forward to seeing you in the next video. Have a great day.